Hello, my name is Davis Binger, and let's talk about integration in polar coordinates. Today we will be looking at problem 3 of the 11.3 handout. We will consider the limestone r equals 3 plus 6 cosine theta, sketch the limestone, and find the area of the inner region. I used a computer program to come up with this sketch, but here's how you can find a sketch without using a program. What you should do is find the value of the limestone at 4 key angles. So the angles you're interested in are going to be 0, pi over 2, pi, and 3 pi over 2. Once you have found the value of the limestone at these three angles, you can use your knowledge of the general shape of the limestone to approximate the remainder of the shape. So at theta equals 0, cosine of theta is equal to 1, and r is equal to 3 plus 6, or 9. So we have our angle 0, we go out 9, and we draw this point here. Then at pi over 2, cosine theta is 0, so we're going to go up from the origin 3 plus 6 times 0, which is just 3. So that corresponds to this point here. For theta equals pi, cosine of theta is negative 1, so r is equal to 3 minus 6, or negative 3. So we're supposed to be going out at this pi direction, but we're going a negative distance, so we track back negative 3, which amounts to coming out here at negative 3. And then at 3 pi over 2, cosine is again 0, so we go down 3. So then you know that a limestone looks sort of like a croissant where the tips are touching, and you can fill in the rest. Now, finding area of a polar region is similar in many regards to finding area between a curve of Cartesian functions. We need to first start by in finding the interval of integration. And in this case, instead of an interval corresponding to x values, we need an interval corresponding to theta values. At what angles does the region exist? Now, we know that the inner loop starts some here where the radius is equal to 0, goes around, and exits after the radius is equal to 0. So the transition occurs when the radius is equal to 0, when our function is equal to 0. In other words, for theta values equal to 2 pi over 3 and 4 pi over 3. Now the general formula for finding the area of a polar curve is 1/2 the integral over the bounds, the function squared. Now we will perform this integral, but by symmetry we can reduce this to the integral from 2 pi over 3 to pi. So let's go back to this picture. We're finding the area of the lower half of this inner loop and then multiplying it by 2. Thus our area is equal to the integral from 2 pi over 3 to pi, 3 plus 6 cosine theta squared d theta. We expand out this expression and we get 9 times the integral from 2 pi over 3 to pi of 1 plus 4 cosine theta plus 4 cosine squared theta d theta. We know the antiderivative of 1. We know the antiderivative of 4 cosine theta. To integrate 4 cosine squared theta, we need to recall a trig identity. We need to make the substitution cosine theta is equal to 1 plus cosine 2 theta over 2. Upon making this substitution, our final term becomes 2 times 1 plus cosine 2 theta. After we rearrange things a little bit, we have an integral for which we know the antiderivative of each term. We integrate and find that our area is equal to 9 times 3 theta plus 4 sine theta plus sine 2 theta evaluated from 2 pi over 3 to pi. This results in the following expression, which I will leave in an unsimplified fashion. Thank you for watching, and as always, if you have a question, please leave a comment below or email me at binger@math.ohio-state.edu. Thank you, and have a good evening.